In this video, we're going to be talking about how to use infrared spectroscopy to identify functional groups within a molecule. So infrared spectroscopy is a valuable tool in the synthetic chemist's toolbox. It can be used to identify a number of different functionalities in molecules and help you confirm a structure of something you've synthesized, something you've identified, or something you're trying to isolate. The units for reading an IR spectrum, and we'll see what IR spectra look like in a little bit, are micrometers or wave numbers. Wave numbers is the more commonly used unit of measurement for an IR spectra. And if we think about what wave numbers represents, this is a frequency. So IR spectra are measuring the frequency of a vibration of a bond. The range from which an IR spectrum goes are about 4,000 down to 625 wave numbers, with the most pertinent information being in the range of about 3,500 to about 1,500 wave numbers. So when we talk about the vibrational states of a molecule, there's various stretches and bends that can occur within a molecule as bonds are vibrating and moving. They can be both symmetric and asymmetric or antisymmetric. We see that asymmetric stretching will cause bands to appear in the IR spectra. And here's a number of different types of modes of vibrational energy states within a molecule. It's less important that you know the different kinds of modes and just know that IR spectra come from bonds vibrating, oscillating, moving in space to cause a difference, a motion in a dipole in a molecule. Functionally, how we take IR is they can be in any physical state, solid, liquid, or gas, usually dissolved in a solvent. We can do them neat or as a dissolved in other compounds. In the lab we have here at AB Tech, we usually run them neat, so if it's a pure liquid or a pure solid. We can also dissolve them in a liquid and use them that way. So when we're talking about the range for an IR spectrum, we go down to about 500 wave numbers and up to about 4,000 wave numbers. The range of about 500 to 1,500 wave numbers is what we call the fingerprint region. These signals are usually pretty weak, and they're usually hard to interpret because there's usually a number of signals that appear in here. They get kind of muddled together, and they are distinct for every molecule, but usually it's hard to determine what is what in the fingerprint region. The region we're more often interested in is called the functional group region. That's from about 1,500 up to 4,000 wave numbers, and that's where all of our functional groups will have their stretching, their vibrational modes. As we see here, there's CC, CN, CO double bonds, we have triple bonds, and we have single bond stretching for different types of different vibrational modes of vibrations within a molecule. So what does an IR spectra look like? So an IR spectra looks something like this. We have over here, this is %T, this is transmission. So what we're actually reading is the spectrum going down. So this spectrum, as you could think of it as being upside down, so it's % transmission. So at a place where it's high up and flat, there's 100% transmission, so there's no vibration going on in this region. And when we have a peak, which is upside down, then we do have vibration in that region. So what we see here is an IR spectra for the molecule hexane. That's a 6-carbon chain with just CH bonds. What we see here is we have some vibrational modes in the fingerprint region. We have a CH and a CC bending because we have CH bonds and CC bonds. And then we see our distinctive stretch for CH stretching at around 3,000 wave numbers, and this would be an identifying peak. If we were to look at this spectra, we could assume that there are really only CH bonds in this molecule, giving us this spectra. If, for instance, we look at a similar but different spectra, methyl hexanoate, we notice that instead of having just a 6-carbon chain, we then have a C double bond O and a CO vibrational mode that will contribute to the IR spectra. And if we look, our fingerprint region is a little bit busier. We have that COC ester stretch. We have a C double bond O. This is a distinctive peak at around 1,700, where carbonyl C double bond O stretches usually appear. And then we have our CH stretching that's appearing at around 3,000 wave number. So this would confirm, if I were to look at the spectra, I would confirm that there's a C double bond O in this spectra, there is a CH bonds in the spectra, and maybe if I was being careful, I could identify that there's a COC bond in the spectra. But again, this fingerprint region is usually hard to determine what's happening down here just because we do have a lot of peaks. Now, I encourage you to look at tables of infrared absorption frequencies. I'm not going to go over all of these frequencies, but just know that within these ranges and a little bit outside of these ranges, there's going to be distinctive peaks that appear corresponding to a distinctive functional group. So for instance, if I see a peak around 3,500, it's generally going to be an alcohol. It could also be an alcohol attached to a carboxylic acid. It could also be an NH peak. So what we see here is infrared spectroscopy is not the most distinct method of identifying what's in the molecule. We kind of already have to know what is in a molecule and use infrared spectroscopy to confirm what's in a molecule rather than use it as a diagnostic tool. So this is usually a confirmation tool rather than something that's diagnostic. But there are distinct regions. So for instance, 3,300 is usually an sp hybridized CH bond. 3,000 is usually an sp2 hybridized CH bond. If we kind of bounce around, we can see C double bond C around 1,600, C triple bond C around 2,200, C triple bond N around 2,300, and so on and so forth. So I would encourage you to, when you're looking at an IR spectra, have one of these absorption frequency tables up so you can kind of pick out what goes where. So now I want to show you what a couple real spectra look like and kind of interpret what kind of functional groups would be within each molecule. So here we have an IR spectra for isopropanol. So we have CH bonds, we have CC bonds, and we have CO bonds as well as an alcohol stretch. So what we see here is in this fingerprint region, we have a CO stretch. That's coming from this bond here, this CO single bond. We also have our CH bond stretching frequency around 3,000. And then this alcohol peak is very diagnostic. Alcohol peaks are usually broad and strong. They appear around 3,400 to 3,500. And this would be diagnostic of an alcohol, this broad, strong peak at around 3,300 to 3,500. So if I were to look at this spectra, not really knowing what the molecule is, I would see this peak down here and say, okay, there's an alcohol, there's CH bonds, there's not much else going on here. This region doesn't really tell me much because this is the fingerprint region. So really all I would know here is there's an alcohol in this molecule. Now to compare, and I know this is a little bit blurry, this is a molecule with a CO, C double bond O, a carbonyl in it. Again, we have the CH stretching frequency, and then we have this distinct carbonyl peak. So C double bond O's appear, C double bond O stretching frequencies appear between 1,500 and about 1,800. They're going to be very sharp and very strong. And this is going to be diagnostic of a C double bond O. So if I was looking at the spectra without really knowing what the molecule looked like, I would say, okay, I have a sharp frequency at about 1,700. That's going to be probably a C double bond O, and then I have a CH frequency, so probably all that's in this molecule is a carbonyl and CH bonds. Again, the fingerprint region doesn't really tell me much because it's got a lot of peaks and I can't really decide which one is which. Now to combine those together, I have butanoic acid. This has got the C double bond O and an OH peak in it, and what that looks like is we have our C double bond O, our strong carbonyl peak at around 1,700, and we also have our broad OH peak that ends up overlapping the CH stretching frequencies. So these combined, this is diagnostic of a carboxylic acid, this CO2H group, where we have both a carbonyl group and we have a broad OH peak with a CH. So if I were to look at this IR spectra and not really know what molecule I was looking at, but trying to identify functional groups, I would say, okay, I have both a C double bond O and an OH that's shifted down to about 3,000 wave numbers. This is going to be diagnostic of a carboxylic acid peak or carboxylic acid functionality in the molecule with really only CH bonds throughout the rest of the molecule. So again, this method of spectroscopy is not really used to diagnose what kind of peaks are within the molecule, but it can be used to confirm if we kind of have an idea of what already is going on in the molecule. It can be used to confirm what kind of peaks we have, what kind of functionalities we have within the molecule that we've synthesized, that we've isolated, or that we're trying to observe.